Hello and welcome to another lesson in our study of Topology 1. So, this happens to be our fourth lesson, and in this video, we'll be going through some explanation and proofs of some theorems and propositions on open sets, closed sets, and clopen sets. So, if you could recall, on our previous lesson, that's lesson 3, we discussed these three concepts: open sets, closed sets, and clopen sets. So there were some propositions and theorems under each of these concepts. Okay, so in this video we are going to explain those which need explanations and those which need proofs. We are going to prove them. Okay, so we are going to try to make this very simple to understand. Okay, alright, so don't forget to like the video if it helps you, and subscribe to the channel so that you'll be notified of new videos. So let's start with the first concept, that's open sets. So on open sets we had these three proposition. Okay, so it says that if we have any topological space, then the full set X and the empty set phi are open sets. And the second one says the union of any number of open sets is an open set, so whether it is finite or infinite. And the third one says that the intersection of any finite number of open sets is an open set. So if you should look at this thing carefully, you realize that it is very similar to the three conditions which has to satisfy before we can say tau is a topology defined on X. Okay, so we are going to explain them, and you realize that they are very simple to understand. That's if you really got the definition of what a topology is. Okay, so you know that when we have tau, okay, when we have tau, before we can say tau is a topology defined on X, then three conditions has to satisfy. And the first of that condition is that we should have the empty set and the full set being elements in tau. Okay, and the second one is that when we find the union of any element in tau, the resulting answer should also be in tau, right? Then the last point was when we find the intersection of any element in tau, the resulting answer should also be in tau. So we said if these three conditions are satisfied, then tau is said to be a topology defined on X. Okay, so in our previous video we defined what open sets are, and we said the members of our topology tau defined on X are called open sets. Okay, so since the first condition for something to be a topological space is to be a topology is that it has to have the empty set in the full set, means that the empty set phi and the full set X are always members of what? Tau, right? And we said the members of tau are open sets. Hence, if we have a topological space, then X and phi are open sets. Okay, so I hope you understand how we did that. Okay, so we use the definition for topology to do that. Then when it comes to the second and the third, okay, it's also very simple, and we are going to use the definition, the rules. Okay, so the second rule for finding out whether something is a topology defined on X is that when you find the union of those elements in tile, you should also get something in tile, okay? And that is what has been framed here, because we know the elements in tile are what we call the open sets. So that is what we have here. And the third one was that when you should find the intersection of those elements in tile, you should also get a resulting answer which is in tile, okay? So that's what we also have here, because as I said, the elements in tile are what we call the open sets, okay? I hope you understand. So when you come here, I said we can get the explanation to 2 and 3 from the definition of a topology tile defined on X. So you can go to the first video, okay, the first lesson we discussed that. So if your definition for topology tile defined on X it was well understood, that means this is very simple to understand, okay? And if you've not watched the third video, the link will be provided at the description area so you can check that. So now let's move on to our second concept, that's closed sets. So for here we are going to do some proofs, okay? But don't worry, we understand them, okay? So we have three things here that we are going to prove. So it says when you have any topological space, then the empty set and the full sets are closed sets. The second one says that the intersection of any number of closed sets is a closed set, so either finite or infinite. And the third one says that the union of any finite number of closed sets is a closed set, okay? So before we go to our proof, let's revise, right, what we learned in the third video about what closed sets are, okay? So we said when you have a subset E, so we have a subset E of X. So this subset E of X is said to be closed if its complement, which happens to be S minus A, is open. And know that it being open means that it can be found in our topology tile, okay? So there's a definition for what a closed set is. When we have a subset A of X, that subset A of X is said to be closed if its complement X minus A is open. And I said it being open means it can be found in tau. So it's an element of tau. So the first one says that phi and X are closed sets. So let's prove the reason why it is so. So you know, by definition of a topology tau defined on X, right? We know that always the empty set and the full set are both open in our topological space, right? And the reason why it is so is because that's the first condition for something to be a topology, right? Then when we should find the complement of phi, right? So that's going to be the full set X minus the empty set phi, which will still give us X. And we know X is always part of our topology tau. If we should find the complement of X, it's going to be X minus X, which will give us the empty set, which is always a member of tau. So you can see that since the complement of phi is open and the complement of X is also open, then phi and X are said to be closed in X, right? So that's why you can see, hence their complements X and phi are both closed in X, okay? So this is the proof for the first one, okay? So now let's go to the second one. It says that the intersection of any finite or infinite number of closed sets is a closed set, okay? So here I want you to take very um I want you to be very serious here, okay, and take some points here. So we are going to use the De Morgan's law to do this, okay? And it's very simple to understand if you bring your mind here. Okay, so first of all, suppose we have a collection of closed sets, right? So we've called that AIs. Then we can apply the De Morgan's law. So we use the first De Morgan's law, and that's what we can see here. That's from equation 1. Okay, so you can see here we have x, and this thing that you see here stands for intersection, then this thing stands for union. Okay, so that's the De Morgan's law. So we are going to use that to prove the second point in a proposition. So you could see that, but from definition we know that since this AI here is closed, that means its complement s minus AI will be what? Open. So this is a complement, right? So but from definition we know that s minus AI are all open since they are complements of the closed sets AI. That point should be well understood, because I said when you are defining a closed set, we say something is closed if its complement is what's open. So since this AI here is closed, then its complement s minus AI will be open. So I hope the first point is well understood. Okay. Then it says hence the union of all our s minus AIs is open since the union of open sets are also open. Okay, so explanation to this point here. Let me give that to you. Explanation to this point here. So the reason why we are saying this is because, from this place, right? We said that the union of any, either finite or infinite, number of open set is an open set. So it is from this point that we are making this conclusion. I hope you understand, right? So from equation A, we can see that this thing here, which denotes the complement of what we can see here, is open. So since the complement is open, and that means this thing will be what? Closed. So that's what we can see here. So this happens to be, so this is the intersection of the subsets, right? Of all our closed sets are also closed, the finite of them. So this happens to be the proof. Okay, so you could see, I know it's a bit technical, but you can understand it. Okay, just try and go over it. You realize it's very simple to understand. So now let's take the third one. It says the union of any finite number of closed sets is a closed set. Okay, so the union of any finite number of closed sets is a closed set. So let's try and do that one. So with that one, we are going to use the De Morgan's law. Okay, a different one. So it says considering the same collection of closed sets AI. So we derive equation below from the De Morgan's law. Okay, so this another equation from the De Morgan's law, and you could see that this is different from the first one. The first one, we rather had intersection here instead of the union, and this intersection was rather union. So you can make the comparison, or we can see that right here. So that's the difference between the two. So let me clean what I have here. So we have this here. So since AI is a collection of closed sets, its complement x minus AI is a collection of open sets. Right? This is very similar to the first point. So from here we can see that the right hand side of equation 2, this happens to be the right hand side of equation 2, is a finite intersection of open sets, which is also open by definition. So the reason why we are making this point, let me enlarge this so that you can see it well. Okay, so the reason why we are making this point, And this point here is what we can see here. So you can see here the intersection of any finite number of open set is an open set. Okay, so it is from this that we are making that point. So that means we see that the right hand side of equation 2 is a finite intersection of open sets, which is also open by definition. Hence, a finite union of our closed set is closed. Okay, so that's also the proof for the other one. And you could see it's quite simple. Okay, now let's move on to the third concept, the last one. All right, so clopen sets. So the clopen sets, we have 3 points here. So it says in every topological space, both the full set X and the empty set phi are clopen, and we will explain why. Then it says in a discrete space, all the subsets of X are clopen. We will explain why. And the third one says in an indiscrete space, the only clopen sets subsets are X and phi. Okay. So let's take the first one. So before we can really understand any explanation, we have to know what clopen sets are, and we discussed that in our previous video. That's lesson 3. So clopen set is just a set which is both open and closed. Okay, so when we say you are clopen, as the name refers, so you are both closed and open. So we know that in every topological space, X and phi are always open, right? So this X and phi are always open. Then okay, let me come here so that it becomes very simple. So here we could see that X and phi, X here and phi here, they are always open. And the same X and phi are also always closed. So that means they are clopen, right? So you can use that alone to say they are clopen. But let me also provide some simple explanation here. So it says from definition, both X and phi are open. The complement of X is phi, right? Which is open. So meaning X is closed. Then the complement of phi is X, which is also open. So meaning phi is closed. So you could see here we said X and phi are both open, and at the same time they are both closed, right? So that means X and phi are both clopen, alright? So that's another way of explaining things. Then we go to the second point, which says that in a discrete space, all the subsets of X are clopen. So we have to know what a discrete space is, right? And I hope you could recall that from our first lesson. So a discrete space is simply so when you have, let me explain it. When you have a set X, okay, and you define a topology tile on it such that the topology tile is a collection of all the subsets of X, then we say that tile is said to be a discrete topology, right? And the space the space S tile is a it's a discrete topologic. Sorry, a discrete topological space. I don't know the reason why I was missing those words. Sorry. So now let's explain this with an example. Okay. So we have a set X to be AB, right? So we know that with this AB, when you should find the subset of X, you're going to get phi X, A, and B. So that means a discrete topology on X will be one which is a collection of all the subsets of X. So we can see we have something here. Then we have to show that all the elements we have there are clopen. So we can see that phi and X are clopen. We've already shown that already, right? Phi and X are always clopen. That was the first point we showed. Then we can see that because this set is in tau is open, That's the point. Then when you should find the complement of that, so the complement of that will be x minus a, which is the set B. And we could see the set B is also found in tau. So that means the complement of the set A is open, meaning A is what? Closed. You can see that here. So since A is open and closed at the same time, then we say the set A is what? Clopen. So we've been able to know that the set A is clopen. Now let's go to B. We are going to use the same concept. So B is open because it's found here. Then when you find the complement of B, you're going to get the set A, which is found in tau, meaning the set B is closed. Therefore, B is clopen, since it is both open and closed. Okay, so you can try that with when you have the set X equals ABC, right? So no, because you have three elements here, your subsets, your number of subsets will be 2 raised to the power 3, because it's always 2 raised to the power n, which will give you 8. So your tau will be a collection of all the 8 subsets. You realize that every subset there will be every element there will be clopen, both closed and open. So you can try that. Then let's go to the last one. So the last one says that in an indiscrete space, the only clopen sets are the full set X and the empty set phi, right? So you have to understand what indiscrete topology is. Okay, so an indiscrete topology is the smallest topology you can ever have. We've discussed this from our first video, and it always has just two elements. That's the empty set and the full set X. So that's what an indiscrete topology is. It always has two elements, the full set X and the empty set phi, right? And we know that this is both closed and open, is clopen. Then this is also both closed and open, clopen. So that's the reason why we say in an indiscrete space, the only clopen sets are X and phi. Okay. So yeah, we explain this with an example. So no matter what X is, always our indiscrete topology, tau defined on S is phi X, and phi is both clopen and X is both clopen. So that's a simple explanation to that. Okay. So I hope you got everything. If you didn't get it, you can always go over the video. The understanding will come. Okay. So our next video is going to be on limit points or accumulation point and closure. Okay. And see you soon. So all the best. Don't forget to like the video and please subscribe. Thank you.